Okay, 1.4, inductive reasoning. Tony's not here. Okay, inductive reasoning is just thinking about things, making conjectures, and we'll talk about what a conjecture is here in a second. This is not on your slide. This is something for us to think about. When the points on a circle are connected, the line segments divide the circle into a number of regions. Okay? We have number one. We just have a whole circle, yes? And I know they look like ovals to you, but that's because it squishes it up on the screen. Okay? They're circles. When I have one segment, when I have one line, how many segments do I have? Two. How many regions, I guess? When I have three segments, how many regions do I have? Four. And then I have how many segments here? 1, 2, 3, 4, 5, 6.
8, 7.
I have 8 regions. Okay, so how does the number of regions change when there's another point added? What's happening?
It goes up one.
It goes up 1.
Like the side
There's
goes.
2 with 1. There's 4 with 3. There's 8 with, I guess if we're talking just points, okay, with 4 points we have 8 regions. So I have 2 points, I have 2 regions, yes? 1 point, 1 region, 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions. What do you think is going to happen with 5?
10.
10.
25.
Okay. So if I add one more point,
So every time you add a point,
so every
you
time
multiply by
I'm going to add a point here, yes? Let's see, I add a point right here. Does that work? Okay. So if I add a point there, it looks like every other point needs to connect to that point, correct? So this one would need to go there, yeah? This one would need to go there. This one would need to go there. And that one would need to go there, right? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hit 16. That's what I counted. So I have 1, 2, 4, 8, 16.
It's times by 2 every time there's another point.
So
now if you put 6 points in there, it would be 32.
So if you think if I put 6 points, we get 32. Why are you guys' computers open? Okay. You guys agree with Cody's conjecture? His prediction?
Yes.
Okay, so did we critically think about that? We did an experiment, right?
Yeah.
We counted. We
I just did that.
we did math. Okay, so we think 6 points would be 32.
Yeah.
And so that'd make 7 points.
49.
Double it, 32, 64.
Yeah.
Right? So, okay. So we've got, this is inductive reasoning, guys. We just did it. So there's some things we need to know about it. So your first gap on there is inductive reasoning, a type of reasoning that reaches conclusions based on patterns from specific examples or past events. So those are your first blanks. Inductive reasoning. Inductive reasoning is a type of reasoning that reaches conclusions based on patterns. Patterns from specific examples or past events. Did we have specific examples on the last slide? Yes. Did we look for patterns? Yes. Okay. So that is inductive reasoning. That is what math is, guys. Especially in geometry. As we get going, every problem should be like a puzzle. You need to look at it. What do I know? What can I do? Sometimes the answer is on the left, but I have to start way over the right, and I have to build to get it. Okay. So example, determine what appears to be the next two terms in the sequence. So we're going to do some experimenting here. You got room to experiment a little. So So we got 800, 400, 200, 100. What's happening?
It'd be 0.
It's even.
It's dividing by 2.
Yeah.
So multiplying by half
Yeah.
with the same thing as dividing by 2, right? So we're thinking that it's 1/2 a sub n minus 1. And what that means is 1/2 the previous term, right? So half of 800 is 400. Half of 400 is 200. Half of 200 is half.
8n minus 1.
50 and then 25.
Would be 50. And then half of 50 would be
It's not bad.
25.
Yeah.
Can I keep doing that forever and ever and ever?
Yeah.
Yeah. And my next one actually would come out to be 25 over 2, wouldn't it?
Sure.
Because it doesn't go in there evenly, does it?
Yeah.
And the next one, when I multiply by half, would be 25 over what? What's 2 times 2?
4.
4. And next one would be 25 over
8.
8.
16. 32. 64.
Okay, so could I keep going forever and ever and ever and ever? So this is, our prediction is it's 1/2 a sub n minus 1. And that's a sub, it means down, and n minus 1 means the term before it. Is that what we did? Yes. Okay. What we just made is actually a recursive definition that we're doing in Algebra 2 right now. So this does lead over into Algebra 2. Okay, so the next one. I subtracted. That's what I did. I subtracted. I did 800 minus 400 minus 200. I don't know why I did that, but it doesn't even work. Mine didn't even work, so I had to go back and do it again.
Why did you do that?
I don't know. You guys were better at it than me, I guess. So the next one we have 18, 24, 32, 128 over 3.
Wait a minute. How'd you go from 132? How'd you go from 30?
We got to figure it out.
But
It's not wrong. There's a pattern there.
well, you're adding
Maybe
8.
timesing it by 3 because 3 times
Where the heck did you get 8?
Well, 3 times 18, 3 times 18 is not 24.
No, 3 times
Nani?
3 times 6 equals 8. Is it? 3 times 8 equals 24. 3 times.
That doesn't, no, but you're doing it right. She's like, well, 3 times 6 gave me 18. 3 times 8 gives me 24. And she's like, oh, wait, 3 doesn't go into 32. So she's trying something, yes? There's nothing wrong with that. So you got it, it failed. Guys, math, mistakes allow thinking to happen. If people did not make mistakes, we would not have the math we have today. You would not have the cell phone in your pocket or in your hand or laying in front of you. You would not have it if people did not make mistakes. Yes?
Could you times that by 2, like 9 times 2 times 2 is 18, and then 12, and then 16, and then would be like 60.
Yeah, but we got to have a pattern. Like, we have to have something that works for everything. You can't just throw in random numbers.
What about
I'm not throwing them random numbers. Get it.
2 times 9 equals 18. 2 times.
That's
What times 1
what I'm
equals
saying.
4?
Math.
What times 4?
European math. Remember.
Okay, how did you guys figure out it was 1/2?
Wait, what about
Well,
9?
because you looked at it.
Because we looked at it.
Okay, let's go back. Oh, back to it.
I got a question.
What?
What about 9?
What about 9?
Okay, are you able to put it in there?
How? Just tell me. How?
I forgot.
I might be thinking.
What?
9 doesn't go into 24. 9 doesn't go into 32.
I was like, never mind.
Okay, so how did mathematically, let's go back and look. You guys did this. You just don't know that you did it. How did you get 1/2?
You looked at it.
Because half of 800 is 1.
Okay, so basically you took 400 divided by 800, which is what?
Which is 2.
1/2. And 200 divided by 400, which is what?
1/2.
1/2. And 100 divided by 200, which is
1/2.
1/2. Okay, you did that in your head, yes?
Yes.
And didn't know you were doing it. So why haven't you done it with this?
Because there's a fraction in the equation.
It doesn't matter.
Thing we do.
24 divided by 18 is what?
I don't know.
It's
I'm gonna be honest. I don't know, Chief.
What reduces it? It doesn't, 18 does not go into 24. What goes in both 18 and 24?
4.
Bigger.
2.
4.
No. 6.
So
6 is what?
4. and
It's 4
3.
and
4/3.
Do
Yes?
that.
Okay. So 32
Get this.
over 24.
24. We see this.
4/3.
4/3. 8 goes into it, doesn't
yeah,
it?
That's what I'm saying.
Uh-huh.
Okay. So then I'd have to take 128 over 3 divided by 32.
What?
Yes?
Yes.
Well, when I divide fractions, I have to multiply by the
Reciprocal.
reciprocal.
You multiply.
Okay, shh. The reciprocal of 32 is 1 over 32, correct?
Yeah.
Uh-huh.
Okay. Well, something goes into both 128 and 32, doesn't it?
Probably.
Probably 4 does at least, right?
Yeah.
So that would be 8 and 32. Does 8 go into 32?
Yeah.
How many times?
4.
4. So what did I get again?
4/3.
4/3. So it's 4/3 the number before it. Now, on A, you just saw was 1/2, didn't you? You're like, oh, it's 1/2. Is everything going to be that obvious?
Yes.
No, it is not. So we got, the factor is we got to multiply it by what? 4/3.
Yeah.
So we got 128 over 3 times 4/3. Now, does 3 go into 128?
Yes.
Yes.
How do we know if 3 goes into a number?
The
Because
first two numbers.
well, it was.
What's the divisibility rule for 3? If you add all the digits up,
And it equals an odd number.
no, and it equals a number 3 goes into.
It works.
So 1 plus 2 is
11.
3,
It's
and
11.
3 plus 8 is 11. Does 3 go into 11?
No.
No. So does 3 go into 128?
No.
No. Okay, Cody, you're responding. When I ask, it's not always an instant response I want, okay? Other people need to catch up. Yes?
But can't you cancel off the 3s because they're both the same?
Cody, stop. That's not what I'm saying. What?
But can't you cancel off the 3s since they're both the same?
No, because the 3s are in the denominator. In the denominator, you have to multiply them. And we don't cancel, we reduce. Okay, so 3 does not go into 128. It does not go into 4, so we have to multiply across. So 3 times 3 is 9.
I was
And then 4 times 8 is 32, so I put a 2, carry a 3. 4 times 2 is 8, plus 3 is 11, so I put a 1, carry a 1. 4 times 1 is 4, plus 1 is 5. So I just multiplied 128 by 4. I just did long multiplication short. Remember I did long division short? I just did multiplication what? Short. So, how am I going to get to every number now?
times by 4.
4/3.
Times by 4/3. So you yourself times that by 4/3. All on your own. Hint, 3 does not go into 512. Multiply it. No, it does not, because that's 10 when you add it up. What?
Oh, never mind. I wrote the equation. I put a 3 instead of 4.
Well, okay. What's 4 times 2?
8.
8. What's 4 times 1?
4.
What's 5 times 4?
But see, it threw me off for a second because I wrote 13 instead of 12.
Oh.
It made my life real hard.
Okay. So, are these patterns always going to be slap you in the face obvious? No. Now, I didn't pick patterns that were addition, subtraction because those are pretty easy and you can see them, right?
No.
So, I wanted to pick something that made you think.
Oh, 9 times 3 equals 27. Got it.
Your problem back there?
You're trying to fly.
I know, it's been annoying all day.
I see him over there.
Okay, so here are your steps on your paper. Your steps. Your first one is observe the data. That means look at it. Is that what we did on the last one?
Yeah.
Yes. Then it says find a pattern. Did we find a pattern?
Yes.
Did we make a conjecture?
Yes.
Yes. And you don't know what a conjecture is? You're still looking at me like I'm crazy? A conjecture is an unproven statement or rule that is based on inductive reasoning. Okay? So Gracie made a conjecture. She's like, oh, it's 9. They're multiples of 9. And then it fell apart like the third one. Or something like that. Okay? Are conjectures wrong sometimes?
Yes.
Yes. But you got to make one. And then when it's wrong, you go back and start over. Maybe you need to observe it a little bit differently. Until I threw out there what you had done on the first one, just subconsciously, did you know that's what you were doing so you could apply it to the second one? No. But now that you know that, when you can't just see add, subtract, or multiply, you might need to put those ratios and figure them out. So the first thing you're going to do is observe the data. You're going to find a pattern, and you're going to make a conjecture. Is that too small for you to read back there, Landon?
I missed the two bottom ones on the first part of it.
Oh. Okay, and I didn't write conjecture on there, but if you want to off to the side, you can. If you still don't know what a conjecture is, what would you say conjecture was in your own words, Austin? In your words.
Kind of like a hypothesis.
A hypothesis. Ooh, another big word. Can hypotheses be wrong?
Yes.
Yes, they can. You can reject or accept them. Okay? Actually, it's not accept. It's do not reject or reject, right? What's another way you could say it, Brandon? How would you tell me what a conjecture was if I asked you? Just in your own words. Give me the, conjecture for dummies definition. I don't know what it is.
Dummies?
No, you know those books like Algebra for Dummies.
No.
You're not sure?
I'll
Cody, what do you got?
It's like a prediction.
A prediction? Okay. You know what I would say if somebody asked me? It's a guess. Is it a guess?
Educated.
Yeah, it's an educated guess. It's a guess based on looking at patterns, right? So when I ask you for those your own definitions, guys, I'm asking for your own words. If another student came up to you and said, "I just don't get what Miss Mick is talking about. I don't get what a conjecture is." Well, it's an educated guess, isn't it?
Yeah.
Okay. So I've got to use those math words, but we also have to translate it into things that mean something to us as well. Correct? Am I good?
Sure.
Okay. So I want you to look at this. How many dots are in the 5th and 6th terms of this pattern? What is your conjecture? What conjecture can you make about the number of dots in the nth term of the pattern? So I'm going to give you guys, just on your own. I'm going to give you, 3 minutes to think about it? You got 3 minutes. It's on your paper. Okay, does anyone want to share with us what you've come up with for your 5th and 6th numbers, amounts? Sebastian, what'd you come up with for the 5th? The 5th one.
Yes, fashion.
You didn't come up with any prediction? Amanda, did you?
Yeah.
What-
29.
29. Okay. Okay, on the 5th, he thinks 29. Okay, Olive, what did you get for the 6th one? 41. Did you get 29 for the 5th? How many people got 29 for the 5th? See hands. So 1, 2, 3, 2, I can't even count. 2, 4, 6. Are you going to raise your hand?
Yeah.
8. So 8 people got 29. How many people got 41 for the 6th? The same. Okay? Felicia, what'd you get for the 5th one?
Well, I didn't do this right because instead of counting it,
Mm-hmm.
I could have, because, it's simple, because the top part, if you see it for 2,
Mm-hmm.
has 1
Mhm.
on the top, and then there's 4 on the bottom.
Right.
I didn't even realize that.
And then you add that, and then you
Yeah.
got 1,
That's-
2,
that's just
3, and
fine.
4. So 5 is 4 on top, and 6 is 5 on top.
Okay, but what
So
about
when,
the box underneath it?
what do you mean?
Like-
underneath it?
this right here. What do you
Oh,
notice
yeah,
about?
That actually is like 3 times 3.
Okay.
Or 4 times 4.
Okay, so what was your number for 5? What'd you get?
I decided to times it, and I was like, alright, so there's 5, and I times it by 4, and that's 20, and then I was like, well, there's 4 more.
Okay, but this box right here is 4 by 4, yes?
Yeah,
And this box is 3 by 3,
yeah.
and this box is 2 by 2. So the next box should be by 5 by 4. It should be 5 by 5
But
plus your 4.
how I did that was that I was taking the top and the bottom.
Right.
times
No,
it plus
I know, but you times 5 times 4 instead of 5 times 5.
Yeah.
You were doing it right.
It's
Okay. The way Felicia did it is how I figured it out. I saw this was 2 by 2, 3 by 3, 4 by 4. So my next box had to be what? 5 by 5. And my top row went 1 to 2 to 3. The next one is going to be what? 4. That's how I figured it out. So 5 times 5 plus 4 is 29. And the next one is going to be 6 times 6 plus what? 5. And 6 times 6 is 36 plus 5 is 41. Now, did somebody else do it differently and end up with... Yes, Gracie?
I did it differently.
Okay, what'd you do?
Okay, so I did the 1 and then I counted the little dots and then I put 5 and then 11 and then 29. And then I was thinking of what number would 1 to 5 would equal 4. And then 5 to 11 would equal 6. And then 11 to 19 would equal 8. Well, then if you do 4 to 6 equals plus 2. And then 6 plus 8 equals plus 2. And then what you would do is you would take 19 plus the 8 that you already had, and then plus that by 2. And then you would get 29.
Whoa.
What did you just
She,
say?
okay, no. She got 29. She got the same answer as me, right? And I said 2 by 2, 3 by 3, 4 by 4, 5 by 5. But did that make sense to her?
I don't
Okay.
know.
Did it make sense to anybody after the first 2 words? Was I the only one that was lost?
I was
Okay,
listening.
but you know what, Gracie? You're not wrong because did you still get 29?
Yes.
Okay.
No.
So,
Yes.
so this is what I'm talking about. When you guys don't understand, when you don't understand what I'm saying, should you raise your hand and say, Mrs. Mick, can you say that in another way?
Yes.
Because is there usually another way to say it? Because I don't even want to look at what Gracie's got on her paper. Her brain today made sense of that. My brain lost it after 2 seconds. I was like, okay, I'm really trying to follow.
It's barely even any words.
Okay, but her brain did it. But when I was trying to follow her, I was looking at this and I was going, you lost me, like in 2 seconds. Okay, did anyone else come up with 29 with a little bit different reasoning? Okay, so it is 29 and 41. So we need to come up with equation. Next is what is a conjecture you can make. So I'm going to say our conjecture. I want us to write an equation. Okay? Good? So when n was 1, and n just means the number of terms, we had how many dots? 1. So this right here, this term we're going to call n. So n was 1, we had 1. When n was 2, we had, what is this, 5?
Yeah.
And then we had 11, and then 19, and then 29, and 41. Okay? So this is n is 4, n is 5, n is 6. Got it? So we need to figure out an equation. When I plugged in 1, I got 1. When I plugged in 2 to this equation, I got 5. Now, we did this in 2 different parts, yes? 6 times 6, then added 5. 5 times 5, then added 4. 4 times 4, then added 3. 3 times 3 and added 2. 2 times 2 and added 1. And then it was 1 times 1 and added what? 0. Okay, so we're going to have 2 parts to this, yes? We're going to have a multiplication part and an addition part. So how are we going to show that multiplication part? We plugged in a 1, so we did 1 times 1 plus 0. Plugged in a 2, we did 2 times 2 plus 1. 3 times 3 plus 2. 4 times 4 plus 3. Thinking math, guys. N is my variable. What did we do to the variable the first thing? Which is called what? Timesing something by itself is doing what? Starts with an S.
Multiplication.
It starts with an
Subtraction.
What?
Substitution.
squaring.
Subtraction.
Did we square it?
Sure.
Guys, look, this is why it's
Yes.
called squaring.
Yeah.
3
Yes, we did.
by 3. Did we square it?
That's an L.
Yes. So we took n squared, yes. N was 1, 2, 3, 4, 5. Got it? Okay. So then what did we do? We added,
Well, don't rub my leg.
shh. If n was 1, we added 0. If n was 2, we added 1. If n was 3, we added 2. If n was 4, we added 3. If n was 5, we added 4. N was 6, 5. So what did we do to every N.
You
Added
added
by
the
one.
one below it.
1 less? So how about just n minus 1?
Yeah.
Does that work?
Sure, you just made this a lot more difficult than it would be in my head, but yeah.
No, because right now we did 1 through 6. What if I want the 128th term?
What?
How about no?
You want to take? Do you want to do this pattern out?
No.
No. So if I wanted the 128th term, I'd say 128 what
Times
Squared. plus
plus
128 minus 1 would be 127. And then all I would have to, I took something, I didn't make it that complicated. I wrote an equation that will work for every single time, didn't I?
Yes. Yes.
Okay.
Yes, you did.
So
Wait,
this is our,
Oh yeah, never mind.
this is our conjecture. Did we prove this?
Yeah.
No. Okay, we gotta think about it. Get it. Get it.
We just got the
Did you
high-
kill it?
Just use my notebook.
Okay. Shh. Did you get it, Sebastian?
Yep.
Good. Thank you.
Yeah.
Okay. So when we prove something, Alex, can you please remove your chair? Okay. When we so much for work time today. When we prove something, we have to prove it every single time. But guess what? If I disprove something, how many times do I have to disprove it?
500 times.
Once. If I say 2 squared equals 4, so 2 times 2, I have to prove that that's 4 every time. Okay? If I prove every even number times an odd number is an even number, I got to prove it every time. But if I find one case, I've disproved it. Does that make sense? So we have not proven this conjecture, hypothesis, educated guess. We've had said it works for this group. Yes? And to say that it works all the time, we'd have to prove it for all events. And we're not going to do that. But we're going to look at some other ones. This top one is not on there. This top one is not on there. Okay. Based on the data on this table, how many residents would you expect to vote in the 7th town council election? So the first year we had 3,500 residents, 386 voted. It's not on your paper for the 4th time. I want you to pay attention up here. If I have year 2, I have year 2, there's 3,790 people, only 414 voted. I have year 3, I have 4,500. Do you see the page? You look at it.
Yeah.
Okay, so what is your conjecture about how many people voted? I want a hand and I want a reason. How many people do you think are going to vote? There's really not a wrong answer unless you tell me 2. Landon.
I'm gonna say like 800 something.
800 and what?
I know it's
84.
Okay, 884. Why did you say 884, Landon?
Because you can tell it's going up by 100 and it's going up by 20.
So every 100 it goes up, it's about 20 that more vote. Okay. Cody, what do you think?
It's 884 because every voter goes up 114 every year.
So they're going up 114 every year?
But that one didn't.
That one didn't. 555 to 623 isn't. Okay. But we're not totally off, right? Randy, do you have a... Did you have your hand up?
No, I was just.
Okay. So 884, would you guys say that's pretty good?
Yeah.
Okay. Do we have, I mean, really, when you were talking about people and who decides to go vote, is there a lot more than us just looking at a pattern to figure out who's going to vote? Yeah. But we're just making a conjecture. 884 sounds good to me. That's not bad. Okay. It's probably tied to the number of residents more than the number of going up, right? So it's probably more directly tied to how many more people there are. But I'm okay with that. Now, if I would have said 1,000, that would be not a good conjecture, would it? No. That would historically, my patterns would not prove that. And I'd say, 1,000 because they drove everybody to the polls. But that has nothing to do with us looking at this data, does it? Nope. Okay, the next one, I want you to, based on the data about how many numbers would you expect the chess club to have the 5th year? I want everybody to make their own prediction. This one should be a little easier.
Shut.
I'm going to say 26. What do you guys say?
28.
28?
Yeah.
Okay. I said 26. You said 28. This one went up 3. It went up 4. So went up 5. So you said 6, right?
Yeah.
Okay. So yours is probably a little better than mine, right? Okay.
We're smarter than you.
I know.
On to that one.
Okay. Counter example. This is your next blank. A counter example is an example that shows a statement or a conjecture is false. So you proved them wrong. Because I have to prove it right every time. Sebastian, put your chair down. But how many times do I have to prove it wrong? Once. Okay, so a counter example. So I have here, conjecture. A polygon with diagonals has 2 fewer diagonals than sides. Quick. So a polygon is a closed object. Okay? Oops. Closed object. So a square, a rectangle, there's 4 sides, but there's how many diagonals? 2. Okay, so that's not a counterexample, is it? So a counterexample is something that proves it wrong. What about a hexagon? Let's see how good of a hexagon I can draw.
You can draw very fantastic.
Okay, so hexagon has 6 sides, yes? That's a 6-sided figure. So that's 1, 2, 3, 4, 5, 6. Can I stop already?
It'll be 30. Yes.
So did I just prove it wrong?
Yes.
Yes, because this says a polygon with diagonals has 2 fewer diagonals than sides. That is not true, is it?
Yeah, it'll be 30.
It's going to be a lot. Then there's actually a formula. Did I just prove it wrong?
Yeah.
Yes. So every vertex has 4 coming off of it. So there's 1, 2, 3, 4, 5, 6 vertices, yes?
Yeah.
So there's going to be how many diagonals? 24. So did we prove it wrong?
Yeah.
Is that a counterexample?
Sure.
Okay. So the sum, and yours you got to put sum, I think, because yours says sun, doesn't it? Maybe not. Maybe it's on the next one. The sum of 2 composite numbers must be a composite number. You know what a composite number?
No.
Composite is like, it's made up of more, it's not prime. Like 4 is 2 times 2. Okay? So prime is 1 in itself, like 3, 2, 7, 13. Okay. What about 4 and 9? Oh, 4 plus 9, excuse me. Sum. Okay, those are both composite numbers, yes?
13.
That would be 13. Is 13 a composite number?
No.
Nope, 13 is a prime. So did we find a counterexample?
Yes.
Yes. Now, I could probably find lots of examples where it worked, but all I need to find is what?
One that's wrong.
One that's wrong. Makes sense what I'm doing, guys?
This one's easy.
Okay.
I kind of do.
The next one, if we don't get through all 4, I'm not worried about it. They're just examples, okay? A polygon, we got to find something We either say it's true and find a couple of examples to say it's true, or find a counterexample that it's not. Got it? A polygon with 4 congruent sides is a square. Anybody think of something that's not and has 4 congruent sides?
Oh, no.
A square.
A rhombus. That's exactly right. A rhombus. Well, whoever said it. A rhombus has 4 congruent sides, but is it a square?
No.
No.
Squish it a little bit less.
We got to put the ticks to make sure they're congruent, right?
Diamond.
Okay, this is the one where you guys have sun instead of sum. You need to make it an M. Okay, if a number is a multiple of 9, the sum of its digits is a multiple of 9. If a number is divisible by 9, the sum of its digits, so 9, 8, I can't think. 1, 0. Okay? 9, 8, 1, 0. If I add those numbers up, I get what? 18?
28.
18? 9 plus 8 is 17 plus 1 is 18. So let's see if it's true. 9 goes into 9 how many times? 1. 9 goes into 8, 0. 9 goes into 81 how many times? 9 and 0. Okay? So that's a true statement. Okay, so the other two were just examples. So you have enough to do everything, guys. Today's and tomorrow's. Got me?